In this video, I am going to talk about the process you would use to create a potential energy versus displacement graph from a force versus displacement graph. So in this example, I'm going to use an object that's above the surface of a hypothetical planet here, and I want to say that the force acting on it is 10 newtons, and it's a constant 10 newtons. So no matter where you move it or how high above the surface, the force is still 10 newtons. So graphically, force, and this is the magnitude of the force because the direction is downwards or negative, but the magnitude I'll say is 10 newtons, so it's a constant 10 newtons here across. I'll just go to 5 meters here, and I'll graph that constant 10. And the energy versus displacement graph is created by looking at areas under the force versus displacement graph. So if I look at this first meter of distance here, the area is 1 meter times 10. So why area? Why 1 times 10? Well, let's take a look here. If I were to raise this object 1 meter above the ground and drop it, it'd have some potential energy, which we're trying to define. And if I dropped it, it would be transferred into kinetic energy or energy of movement. If I raised it to 2 meters above the ground, it'd have more quote-unquote energy, potential energy that could be transferred into kinetic energy and go faster. And 3 meters and 4 meters and 5 meters. So it seems like the force and the height above the ground or the distance play a role into how much energy it has. Now why it's multiplied, base times height, versus this squared divided by that, or this square root times the cube of that, is a different story. But part of your lab is to determine why that is. So needless to say, 1 times 10 is 10, so I'll graph that data point. The next 1 meter of distance to get us to 2 is another 10 joules, so that's 20 joules there. If I go to the next meter, 30. So this is pretty straightforward because it's a constant force. And that gets me to 40 and so forth, and then the next one gets me to 50. So if I plot this data, it looks pretty nice and neat. It's a straight line, and it goes up there like that. And so what this tells me is at any height above the disk from the planet's surface, I can tell you how much energy it has, how much potential energy. This should be potential energy. 2 meters, 20 joules, 3 meters, 30 joules, 4 meters, 40 joules, and so forth. So I can tell you how much energy it has. And from that energy, that potential energy, I can tell you how much will be transferred into kinetic energy and how fast it's moving and whatnot. Actually, this force that we're just looking at is actually the potential energy on Earth. It's actually, the equation is mgh. So if you look at this, it looks like a straight line. It looks like y is equal to mx plus b, where the slope, this is the slope m, not the mass. The slope m is actually mg, the force, 10 newtons. If you look here, it's 10 over 1. The slope is 10. So physicists use these quantities to determine quantitative equations that we can use to predict things. Again, why is it base times height for the area and not something else? Again, that's part of the lab. You're going to be investigating elastic objects, which would have a force versus displacement graph that looks something like that, probably. Depending on the spring constant, it might be higher slope or lower slope, or you might have force that act quadratically, whatnot. Again, the concept's the same. So for the straight line, we're dealing with triangles here. So the area in the graph would be there, and we'd find that area and plot that number. If it's quadratic or curved of some sort, you'd have to use integral calculus. However, there are rules for that and how you do that. You can actually find the area exactly for a certain range on the graph. But the concept, again, is the same. Area in the graph gives you the potential energy, which we can then talk about transferring to different types or different forms of energy. So that's the process you would use to create a potential energy graph from a force versus displacement graph.